This is review lecture number 4 of our online review course of an undergraduate probability and statistics class. I'm Chris Mack, the professor for this online review course. And we are about to start 3 parts, 3 different lectures on the topic of probability. We often hear the words probability and statistics used together as if they are somehow joined or related, and of course they are. Probability is, in many respects, one side of a coin with statistics on the other side. Since we use coin flips a lot to illustrate probability, that's an apt metaphor. What is probability? It's a mathematical framework for reasoning about uncertainty. This sounds a lot like what we said statistics was. Statistics is a little broader than just probability, but probability underpins much of the mathematics that we use for our statistics. And as we'll see later, probability distributions create a fundamental mathematical tool that we use to develop confidence intervals and to do hypothesis testing. And a thorough understanding of probability is essential to really understand how and why statistics works the way it does. Now, but before we get into the basics of probability, and certainly before we get into how probability is used in the field of statistics, I'd like to just talk about what probability means from the perspective of science and physics and engineering. Most of the problems that we work in engineering and in science tend to be deterministic. Think about your freshman year physics class, or even your high school physics class, where you had to work a problem of shoot a cannonball out of a cannon with a particular initial velocity and a particular angle, and then calculate where does it hit. And you work through the math and the theory of force and gravity, and you come up with an answer. The cannonball hits this distance away from the cannon. Well, the answer was a number, a single number. The equations were deterministic. There was no probabilities involved. There was no uncertainties involved. Given the same inputs, we always get the same outputs. This is most of what our engineering solutions and our scientific theories give us, deterministic answers. But that's not really the way the world works. Life is messy. Everything has uncertainty built into it. There are 2 basic ways that we use uncertainty to modify a deterministic theory of the world. One is randomness simply adds uncertainty to our deterministic solution. So I've got an equation that says given the initial velocity and the angle, this is where the cannonball will land. But if I have some uncertainty in the initial angle or the initial velocity, that will propagate to become uncertainty in the final answer. If there's some other uncertainties like wind resistance or changes in wind resistance, air resistance and wind, that can add uncertainty to the answer as well. But basically we have a deterministic approach to the problem, and then we tweak it. We add uncertainty to the inputs and the outputs and measurements and such. This is maybe the most common way that we use randomness in physics and engineering. But there are some other situations where randomness completely dominates the outcome. Just think about quantum mechanics, where everything is a probability distribution. But when you get down to the molecular level, even without quantum mechanics, you can think of things on a molecular level as being dominated by randomness. So that what's the reaction rate of chemical A with chemical B? We can write down what looks like a deterministic rate equation, but in fact what we're writing down is the probability of A and B reacting. And on a molecular level, it's completely probabilistic. So Probability is fundamental to the way science and engineering works. So even if you weren't thinking about statistics, it's very important to have a good foundation in probability if you want to do any real work in the world of engineering and physics and chemistry. Oh, I'm sure biology, everything gets thrown in there as well. All right. When it comes to probability, I've already mentioned there's two basic views, the frequentist view and the Bayesian view. We're going to talk about the frequentist view here. What is the frequentist view? All right, here's the problem. I hand you a coin, not a fair coin, not a coin that is 50% likely to land on a head and 50% likely to land on a tail, but a coin of unknown fairness. It's weighted in some way that when you flip it, it's more likely to be on a head or a tail. Now, if I give you this coin and I say, you help me figure out what is the probability of getting a head, what would you do? Well, I think most of us would very intuitively know the answer. We would simply flip the coin a whole bunch of times, let's say n times, and count the number of heads. Then we would say the probability of getting a head is something like the number of heads divided by the number of coin tosses. In the limit, as n goes to infinity, we assume we will approach the actual probability for that coin. This is called the weak law of large numbers. And the law of large numbers is the foundation of the frequentist view of probability. Now, there's some assumptions built into this viewpoint. First of all, we assume that each trial results in independent outcomes. That is, if I flip a coin once and I get a head or I get a tail, the outcome of that trial in no way influences what happens the next time I flip the coin. Every trial is independent. Also, we assume that the outcomes are identically distributed. In other words, the probability of getting a head doesn't change from one coin flip to the other. It remains identical. But given those two very reasonable assumptions, which don't always match real experiments or real problems, they very frequently do, then we can apply this weak law of large numbers, calculate the probability based on this frequentist approach. Well, this is all quite intuitive. It matches a lot of ways in which we think about probability and use probability, but not everything. All right? Let me give you an example. We'll often talk about the probability of a unique event. Right? Looking back in history, what was the probability that World War II would happen? Right? What's the probability in the future of some future event happening? What's the probability of an atomic war? What's the probability? This is something that scientists actually work on very seriously. What's the probability that ocean levels will rise by more than 50 centimeters by the year 2100? Well, that's an important probability to get your hands around. We cannot apply the frequentist view to this meaning of the word probability, and yet it is a probabilistic approach. The meaning of probability has meaning, it makes sense, but we can't repeat the experiment a whole bunch of times and see how it might turn out. Here, the Bayesian approach to probabilities will be more valuable, and by the end of the 3 lectures on probability, we'll have discussed a little bit about the Bayesian approach as well. But the frequentist view will dominate our discussion. All right, with that in mind, let's start building a probabilistic model. What is a probabilistic model? It has 2 main elements. The first thing is a sample space. We use the symbol omega, capital Omega, to represent our sample space, and it is the set of all possible outcomes of an experiment. I run an experiment. What are all the possible outcomes that you can get from that experiment? That makes the sample space. Then we also have a probability law, which we give the symbol P to represent. The probability law assigns a non-negative number to each event of interest, which we call the probability of that event happening. There are lots of possibilities for probability laws, but none of them will be useful unless they follow the axioms of probability. Kolmogorov developed, the very famous Russian mathematician, developed these axioms of probability, and we use them today in all aspects of probability theory. There's a lot of mathematical details that go into developing a probabilistic model of some experiment, but we're going to ignore almost all of them and only talk about the very simplest mathematical details. So first, sample space. What is a sample space? It's the set of all possible outcomes of an experiment. Well, what's an experiment? The experiment is the underlying process that produces the result. Now, we will define an experiment as producing exactly one result, one outcome. If you want two outcomes, you have to run the experiment twice. Every time you run the experiment, you get exactly one outcome. The sample space is the set of all possible outcomes, but that sample space may be discrete, or it may be continuous. Discrete might be, flipping a coin where you can get a head or a tail. Discrete answers. Binary in that case. But if you're talking about firing a cannon and seeing where it lands in the XY plane, there's a continuous set of XY coordinates where that cannonball might land. So if we thought of the landing position as a random variable, it would have a continuous sample space. Outcomes are defined as being distinct and mutually exclusive. A head is not a tail is not a head. They are distinct from each other. You cannot have, for example, in the way we use probability laws, a superposition of part head and part tail. Every outcome is distinct and different. And then the sample space, the collection of these distinct and mutually exclusive outcomes, must be collectively exhaustive. That is, once we've listed all of the outcomes, our sample space includes them all. There's nothing left, nothing we've forgotten that could be an outcome of the experiment that isn't listed. The sample space includes them all. So what's some example sample spaces? Here's my experiment. I flip a coin 3 times. And I look at the heads and the tails that result from those 3 coin flips. One important question is, am I defining order as mattering or not? Let's suppose I say order matters. Then what are all the outcomes of my experiment? Well, I can list all the possibilities. So I would say the sample space equals, here now I'll use some set notation. The curly brackets is the set of outcomes. And what are the outcomes? 3 heads, head, head, tail, head, tail, head, head, tail, 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 head, head, etc., all the way to 3 tails as all the possible outcomes from this experiment, where I've defined order as mattering. Of course, that's my choice. I'm deciding what the experiment is, so I can decide that order doesn't matter. Now what's my sample space? Well, I could get 3 heads, I can get 2 heads and 1 tail, I can get 2 tails and 1 head, or I can get 3 tails. A simple way of nomenclature for this sample space would be omega equals 0, 1, 2, and 3, where the outcome is simply defined as the number of heads. Of course, I could have defined it as the number of tails either way, but I need to make sure I clearly define which one I'm using. So you can see when order doesn't matter, I have a sample space of only 4 items, whereas, how many do I have here? 1, 2, 3, 4, 5, 6, 7, 8. A sample space of 8 outcomes if order does matter. Now that's an experiment in a sample space. Now let me define another term, an event. What is an event? An event is a collection of possible outcomes. Now, an event could be one outcome, but an event could be more than one outcome combined. For example, I might say the event is flipping a head, and then as my third coin flip a tail. But I could also define an event as getting an even number of heads, which in this case is only 0 or 2. Or I could define my event as being 2 or more heads. Right? So an event is a subset of the sample space. Now, it might occur to you that we're talking about sets a lot here, and this becomes the mathematical algebra that we use to describe sample spaces and events. Set algebra is, we borrow set algebra and use it in our probability theory. So our sample space, omega, will be the set of all possible outcomes. Then we can define an event, say A, as a subset of the sample space. A different event, B, will be a different subset within that sample space. And this diagram that I've just drawn is called a Venn diagram, very commonly used in set algebra and in probability to help us picture how all of these sets will relate to each other. And we'll find that drawing Venn diagrams will make the concepts of set algebra and probability laws easier to understand. Given that, let's review some of the basics of set algebra. The first thing we'll look at is the concept of intersection. The intersection of two sets, A and B, is, now let me go through what all this terminology means. Opening the curly bracket is the same as saying the set of all. So the intersection of A with B is the set of all x such that x is a member of A and x is a member of B. So intersection is an ANDing operation. And of course we can visualize it very easily. Here are all the outcomes that are both members of A and members of B. And this upside down U is the symbol for intersection. Now we say intersection of sets, but in probability it's the intersection of events, because these subsets A and B are events in our probabilistic model. We also have a union. What is the union of A and B? We use this U symbol to represent union, and it is the set of all x such that x is a member of A or x is a member of B, and we picture it as on the picture on the left. Now, there's some other terminology we use in sets that will be very useful. Disjoint sets are sets that have no intersection. So if A and B are disjoint, they share no elements whatsoever. In other words, A intersects B is the null set. Let me use this symbol here to represent the null set, a set with no elements. A subset, A is a subset of B if every element in A is also found in B. We use the sideways U here to represent subset. So A is a subset of B if the intersection of A and B is equal to A. That's the same thing as saying all the elements of A can be found in B. A partition, if we partition our sample space, what that means is the union of all of the partitions equals the sample space. It's a collection of disjoint sets. A, B, C, and D are all disjoint subsets. They have no overlap, and their collection, the union of all of them, creates the entire sample space. That's called a partition. And finally, another term we use is the complement. The complement of a set is all the elements of the sample space that do not belong to that set. We can use either a superscript C or a line over the top to represent the complement. You know, in statistics we use the line over the top to represent the mean of a variable. So I'm going to use this superscript C in my course here to represent the complement. So the complement of A is the set of all x such that x a member of the sample space such that x is not a member of A. And we can picture it very simply as everything that's not inside A but is in the sample space, that's the complement of A. You can see that these pictures, the Venn diagrams, are very useful for grasping these concepts. So let's look at some set algebra identities. Some very, very simple ones, essentially intuitive. The complement of the sample space is the null set. A complement of a complement gives you the set back. The union of a set with its complement is the sample space. And the intersection of a set with its complement has to be the null set. All you have to do is draw some Venn diagrams and you'll very quickly see that all of these identities are obvious. A little less obvious is De Morgan's laws. And De Morgan's laws say if I have a set of events and I take the union of those events, then I complement the whole thing when I'm done. That's the same thing as complementing the events first and then taking the intersection of all of those events. Reverse the what's a union, what's an intersection, and I get the other De Morgan's law. I'm not going to go through these other than to say, why don't you take a look at an example of two events, A and B, look at the Venn diagram, and convince yourself that De Morgan's laws are true by picturing it, or maybe even drawing, shading in the various two sides of the equation and see if it works out. Other than that, I'm not going to talk anymore about De Morgan's laws. Let's now get back to a probabilistic law. A probabilistic law assigns a number to each event of interest. We'd say P of E is the probability that event E will happen. Well, it's very common to apply what's called the additive law, the additive axiom of probability, to calculate the probability that an event E will happen. What we do is we simply assign a probability for every outcome I in the sample space. Then we look at what outcomes in the sample space are in the event E. Then the probability of E will be the sum of all of these P sub i's, the probability of the outcome I, for all outcomes that happen to be in E. I'll talk about the additive axiom in a moment. But the whole idea of a probabilistic law is we have some event and we simply assign a number that says this is the probability. Probability laws must follow the axioms of probability. And there are three axioms, the Kolmogorov axioms. What are they? The first is non-negativity. The probability of an event always has to be greater than or equal to 0 for every event. There's no such thing as a negative probability. Normalization. The probability of the sample space is 1. No matter what it is, everything ends up being in the sample space. We want all the probability of everything to be 1. And finally, additivity. If I have a sequence of disjoint events, disjoint means there's no overlap, there's no elements in common between the events E sub I. And if I take a union of these disjoint events, the probability of that union is the sum of the probabilities of the individual events. You can recall that we used this additivity axiom when we divided up an event into as a collection of outcomes. Outcomes are, by definition, disjoint, so that I could say the probability of an event is the sum of the probabilities of the outcomes that make up that event. Recall, as I've already said, that disjoint means the same as mutually exclusive, no overlap whatsoever. Given the three axioms of probability, we can derive some probability identities. And these probability identities are pretty intuitive. In fact, we would be a little bit worried if we had a probability law that didn't follow these identities. For example, the probability of the null set is 0. The probability of the complement of some event is 1 minus the probability of that event. The probability of an event is always less than or equal to 1. If E is a subset of F, then the probability of E can never be greater than the probability of F. And finally, if I have two events E and F, I take their union. The probability of that union is the sum of the probabilities of the two events minus the probability of the intersection of those two events. Now, many of these are fairly easy to prove if you're interested, and I'll leave this completely as an exercise to the interested student. You might want to try and prove some of these identities. We're not going to do proofs in this review course at all, but those of you who are overachievers, you may be interested in trying out some of those proofs. Now, how can we apply probability to a real problem? Whenever we map the real world to a probabilistic model, we have choices to make. Sometimes the choices are fairly obvious and sometimes they're not, but they are choices nonetheless. There's nothing about probability law that dictates how we must map the world to a model. First, we have to pick the sample space. Well, what is the sample space? Well, that usually depends on how we define our experiment. It's up to us to decide what an experiment is, and then to, given that definition of our experiment, to elucidate, list all of the outcomes that are possible, and that becomes our sample space. Then we have to define a probability law. There is more than one way to define a probability law. There's lots and lots of ways. We are constrained by the axioms of probability, but beyond that, the probability law, which assigns a number to an event, could be assigning a very large number of possible numbers to each event. So we have a huge range of choices available to us when creating a probabilistic model. We judge the resulting model by its usefulness. It's impossible to say that one model is right and another model is wrong. All we can say that one model might be more useful than another. So let's review. What have we learned so far in the first of our 3 lectures on the topic of probability? As always, you should be able to quickly and easily answer these questions. If not, you should probably go back and review some of the material. Explain the frequentist view of probability. What are the 2 elements of a probabilistic model? What are the defining properties of a sample space? Define the terms disjoint sets, subset, partition, and the complement of a set. And finally, what are the 3 probability axioms? Well, that's our first of a 3 set of lectures on the topic of probability. Part number 2 coming next.